The next one to look at is our K1 factor. Now across that equation they go in number order. So the first one is K1 and it is a duration of load factor. The duration of load factor takes account of the fact that timber is a natural product and each timber member consists of millions of individual fibres. Some of those fibres are going to be a little bit weaker. And over a period of time, as the load is applied, some of those may start to fail. So that as a load has been applied for 50 years or more, we may see some of the fibres have actually failed. And while we can't actually see it with our naked eyes, with a microscope, we would pick up that there's been some microscopic damage to the timber and it has less strength. This is modelled using the K1 factor. And using the K1 factor is as simple as looking up a table. And we ask ourselves, for the load combination that we are considering in our ultimate limit state, what is the shortest duration load in that combination? For example, a combination of permanent loads, imposed loads and wind loads. The shortest duration load in that whole combination is the wind load. And the wind load's only going to last for seconds. And so we're going to look up an appropriate K1 factor for seconds, for a load of duration of some seconds. On the other hand, if we have permanent actions and imposed actions, the shortest duration load is the imposed action, and it depends on the nature of the imposed action as to what the K1 value is. But for example, crowds are not going to exist for a very long period of time, so it's order of days that we're using the K1 factor for. The second of the K factors is the partial seasoning factor K4. And this is really simple. What they have found through a lot of testing is that higher moisture content in the timber means that the timber has lower average strength. And the more we dry the timber out, the higher the average strength of the timber becomes. As a result of that, we take that into account for the service condition of the timber. If the timber is likely to be used in an environment in which it's going to pick up a lot of moisture, we have to use a low K4 factor. However, even before that stage, if we have chosen the right material for the job, it will be close to the equilibrium moisture content. And so if the service environment is for internal applications, then we're going to use seasoned timber and the K4 value for that moisture condition is going to be 1. If it's for outdoor use, we'll use a timber with a higher moisture content initially, and again it will be in equilibrium with its required service. Often the K4 factor is 1 if we've chosen the right material for the job. The K6 factor is a temperature factor. The higher the temperature is, then the more stress each individual fibre is under. So high temperatures can reduce the strength of timber. And as you can see on this map, Australia is divided into 2 zones. In the far northern zone, where it's both hot and moist, the timber does tend to be a little bit weaker. In the rest of Australia, it's the nominal strength. So in the far northern zone, only for seasoned timber, the K6 value is 0.9. For everywhere else in Australia and for unseasoned timber everywhere, K6 is equal to 1. Now the K9 factor is a strength sharing factor, and there is a video that illustrates that with this model of a timber floor. However, the strength sharing factor simply looks at the way in which strength is shared by parallel bending members. And it looks at 2 different systems of parallel bending members. Often when we're using bending members, we've got bridging members over the top that can enable some load sharing. In some cases, we will fabricate a member, and in these 2 pictures you can see some members where we have taken 2 individual members and join them intimately together like this. So in most cases we nail them together, in some cases you might bolt them or screw them together. But nonetheless the 2 pieces of timber are effectively behaving as one. In that case, if one of them has got some small characteristic that is going to reduce its strength, the net effect is going to be reduced by the fact that it's sharing some capacity with its neighbour that may not have a strength reducing characteristic in the same location. So in those cases there, we call it a combined system. And evaluating the strength sharing factor is as simple as counting the number of elements that are in the combined system. So we add them all up together. In this case, we have 2. If we add another one, the NCOM value is 3. And that enables us to calculate the K9 factor. If we've got a discrete system, which is like this, where the members aren't individually touching each other, then the strength sharing is accomplished by the bridging members over the top. And so the strength sharing isn't quite as efficient in that system. And we still count members in order to evaluate the K9 factor. The NCOM is the number of individual pieces of timber that are intimately connected together. The NMEM is the number of elements across the system that can effectively share strength. Now, in the event that this one here, the middle one, fails, it's likely that the load will be picked up by these other 2. So that then, in this case, the NMEM is 3, because there are 3 elements that would be sharing the load in that type of system. I have here an animation that just shows the way this works. This animation shows a single member, a grid in which there are a whole lot of parallel members. That's a classic discrete system. And on the right are 3 members stuck together in a combined system. As we load it up, you can see that they all start to deflect. As they deflect further, we get to the stage where one of the members in all 3 of those systems is going to start to fail. In the single beam, that's the end of the road. There is no extra load that it can carry, and so at that point, that member has failed. But in the other 2 systems, its neighbours can pick up some of the load, so that in this notional experiment, the load actually increases beyond that point where the first element starts to fail. In the discrete system, the sharing isn't quite as efficient as it is in the combined system, so after a while the others are overloaded and they start to fail, whereas in the combined system it can go on a little further. The result of this is that we get an increase in strength of the whole system because of the value of that strength sharing. And in design, we count up the number of members that are intimately connected, the NCOM. In a discrete system, we count up the number of members that can share the load across the discrete system, and we use this table to evaluate some parameters that are used to evaluate K9. K9 will have a value of bigger than 1. So the larger the strength sharing possibility is actually going to increase the capacity of the whole system. The final K factor in the moment capacity equation is the stability factor, and it models buckling failure. There is a video that demonstrates buckling failure in bending members, and this short animation shows the way in which under load the member deflects to the side as the top of it goes into compression, and also the centre part of the section appears to twist as well. So lateral torsional buckling is a real failure mode for timber as it is for a lot of steel sections, and we have to take account of it in its design equation. This K12 factor is a function of the slenderness of the beam. The slenderness here is denoted by an S factor, S1 in the case of a bending member. So you can see if we have stocky members, the rho B times S1 is going to be less than 10, and for that K12 is 1. For very slender members, we have something that gets very close to a buckling formula, and in that case the K12 value is given by the inverse of the slenderness squared. And in between we've got a linear interpolation between the two. The other factor in that equation is what we call a material constant. And it again is something that a lot of research has gone into, because timber is a natural material. It does have some creep involved, and it may not always be dead straight. And if it's a little bit has a little bit of initial curvature, that may reduce the buckling capacity of that particular member. So that the material constant takes those into account, and it is a function of the grade of the material, the bending strength of the material, and the stiffness of the material. We find it by looking up tables in AS 1720.1. The most common table for us to use is table 3.1, but there are other tables that we can access. Some of those involve a ratio of a temporary load to the total load. If we're going to use the ratio of temporary load to total load, we have to evaluate it for each and every load case, because it will be different for each and every load case. If you want to use one value of rho B for every single load case, and you're using one of those tables, use the value for R equals 0.25. And that will give you an appropriate value of material constant to use. The main driver of the K12 factor is the beam slenderness. And this S1 value varies with the type of loading, the type of restraint to the member, whether it's in minor or major axis, and the lateral restraint that is often offered to the member by the other members in the system. And we need to consider very carefully load reversal. Under some applications, and a classic will be a roof member, we will be having downward loads. So any members over the top of that, such as purlins or battens, are going to be restraining the top edge, which under gravity loads will be the compression edge. So that for that condition, we're looking at downward loads. If we think about wind loads, the wind loads are upward direction loads, so that the bending moments are now reversed, and the top edge becomes the tension edge and the bottom edge is the compression edge. However, our restraint is still offered to the top edge, so that there we are restraining the tension edge, not the compression edge. And so lateral torsional buckling and the resistance of a member to lateral torsional buckling is going to be a function of the load direction as well as the way the restraint is offered. For example, S1 with lateral restraint to the compression edge. So this is a classic case for a floor member. We've got a floor member like this, it's loaded using a gravity load, and the top edge is the compression edge, and it has got the floor fixed to it so that the top edge is restrained against lateral movement by the floor. Under those circumstances, we use this expression to calculate the slenderness. And the expression that you see there is a function of the depth to breadth ratio, so the depth of the member to the breadth of the member, and also the distance between the lateral restraints along the top edge of the member. If we look at other systems where you have continuous lateral restraint, so that the top edge is continuously fixed to some restraining element, then what we find is that the top edge, which is the compression edge, can't move at all. And so there is no tendency for lateral buckling, the slenderness is 0, and as a result of that, the K12 value is going to be 1. On the other hand, if we have an element where the top edge is in tension, the bottom edge is not necessarily restrained now. As it's in compression, it can move sideways, and we have a different expression for the lateral torsional buckling slenderness of the member, and that is the one shown on this particular slide. It again is a function of the depth to breadth ratio and the distance apart of the lateral restraints to the member. And if we have continuous restraint of the top edge and it's in uplift, so that that's a tension edge, then we still have tendency for lateral torsional buckling, and that is given by this expression. Now, if we've got a big, very deep member, say as a rafter in a portal frame, and we have uplift on it, the bottom edge is a compression edge and it can be wanting to move sideways. We can stop that by fitting some fly braces. These are braces that go from the bottom edge up to something in the roof structure here that's going to stop that bottom edge from moving sideways. And we can evaluate the slenderness of a system in which fly braces have been installed. And this slide shows some fly braces. and those fly braces are going to stop the rotation of the member, and as a result of that, they're going to enable the member to have lower tendency for lateral torsional buckling. And that's the expression for the slenderness of that configuration. Finally, in this bending capacity is the bending strength, and we've seen that the bending strength can be obtained in different places depending on the product that we're using. In some cases, the bending strength is a function of size. And so we're going to look up a table, and it often tells us that we have to do a correction for the size of the element. Then there's the section modulus. This is the classic elastic section modulus. So for major axis buckling, it's D squared times B on 6. For minor axis buckling, it's in that orientation there, but the same expression.